All right, so we're going to go ahead and get started now with our next problem set. I believe this is problem set number 4. And yeah, let's go ahead and take a look at number 1. And we want to find, in this case, we want to find the limit of this function as x approaches -3 from the right side. Remember, this plus sign right here tells us that we're approaching from the right. So that means that we're only going to be needing to look at values that are greater than -3, which would be values like -2, -1, and 0. So the first thing we want to do is see whether or not -3 is in our domain. If it's not, that's not necessarily a big deal, but if it's in our domain, that makes things a little bit easier for us to start out with. So let's go ahead and plug this in and see if that makes sense. So if I plug in a -3 here, it becomes a 3 times -3, or just a -9, which would just end up being the square root of 0, or just 0, right? So luckily for us, that -3 is in our domain, which means that we don't really have any extra concerns there. So then the easiest thing to do here would be to just kind of recognize with our square roots that we cannot have any negative numbers within this, right? So if I had the square root of -1, that's going to be undefined. And so we don't have a limit there. That would be a limit is undefined. Even though we might technically use imaginary numbers to represent that, it's still undefined in terms of a limit or when we're graphing it. So in this case, since we're approaching it from the right, we automatically know that we're not going to end up with any negative values in here, because that means that all of our values are going to be smaller than this -3, which means if I plug in, say, a -2, for example, I'm going to get 3 times -2, which makes a -6, plus 9, which just gives us the square root of 3 here. And as we get into even bigger numbers, did I say smaller before? We want numbers bigger than -3 because we're approaching from the right, and -2 is bigger. So as we get into bigger and bigger values, obviously if I plug in my -1, that makes us a -3 plus 9, or just a square root of +6. And we're just going to keep going up and up and up like that. So as we get closer to our -3 from that right side, we see that it approaches 0. And I'm going to make our little table over here just to kind of visualize that a little better. So we're going to start with, let's start with our larger values. So we'll start with 0, -1, -2, and 3. So, and -3. Obviously, we found that when we plug in that -3, we get a 0. If we plug in that -4, we get the square root of 3. Plug in that -1, we get square root of 6, just like we did a second ago. If I plug in that 0, it's going to be 3 times 0, or just 0 plus 9. So we get the square root of 9, or just 3. And obviously, the square root of 9 is bigger than the square root of 6, which is bigger than the square root of 3, which is bigger than 0. And so we see as we go here that we're just getting closer and closer to 0 because we're getting just smaller and smaller values as we get closer to this value from the right side. So our limit is 0. If we were trying to approach this from the left side, that limit would be undefined in that case, because that would be entirely values outside of our domain. Because if we were approaching from the left, that would be values less than -3. So that would be, say, x values of like -4 and -5. Well, if I plug in a -4 here, I'm going to get -12 plus 9, which gets us a square root of -3, which is undefined, right? When we go to graph that. Or if I plug in the -5, that's going to get me a -15 plus 9, or the square root of -6, which is again undefined. So we're lucky in that we were approaching from the right side, so this limit does exist, but keep in mind, because we're inside this radical here, any values that would be less than this 3, because it's right at the end of our, right at the edge of our domain, anything less than this would result in this being undefined. For the next ones, The next few problems, it says make the function continuous at the point given if possible and solve. So for this first one, we're going to take a look at this right here. So f of x is obviously discontinuous at x equals -4, and that's the point they're giving us, so we're at a bit of a standstill. So what we want to see if we can do is we want to see if we can factor out this x plus 4 down here. Let's give that a go. Let's see if we've got x squared plus x minus 20 over x plus 4. Well, if I factor out that top bit, that's going to give us, let's see, an x minus 4, I believe, and an x plus 5 over x plus 4, which means that we cannot factor out that x plus 4 like we want to, so we are not able to make this function continuous. It is not possible. There's nothing that we can do there. There's no value at this point. So we're going to go ahead and put none because this does not have a value. If we were to graph that, it would probably, or write it in our calculators, it would probably give us a domain error or say that it's undefined. For this next one, we see that obviously the point they gave us is x equals 9. If we plug in that x equals 9, we get a 0 in the denominator, which makes this undefined, right? So it's discontinuous there. There's a discontinuity. So we're going to try again. We're going to see if we can just factor that out. And luckily, I notice here that this is a perfect difference of squares. So we're going to go ahead and factor that out like this. And you can always double check that by foiling, but I know that that's going to be correct. So in this case, we can cancel out those x minus 9s, and so we're just left with an x plus 9. Obviously, this when x equals 9 is still outside of this function's domain, and that would be considered a whole if we were to graph that. But in this case, we just want to figure out what we want to make it continuous, which we just did, and then figure out what this value will be. So in that case, it's going to be a 9 plus 9, because we're plugging in that 9 for the x. So our answer is 18. And for this third one, we're just kind of doing the same thing. So once again, we see that it's discontinuous at the point they gave us, because if we plug in a -5 there, we get 0 in the denominator. So again, we just want to see if we can factor out that x plus 5. So if I factor out this top bit, it's going to turn into, I believe, x plus 5, x plus 7, which means that we can cancel out those x plus 5s and we're left with this x plus 7. So if we plug in -5 for x, our answer is going to be 2. So that's what the value of the function at that point would be if it wasn't discontinuous at that point, is what we just found. All right, so now we've got this complicated bit here, and we want to figure out what intervals this is continuous on. So obviously it's not going to be a very large bit, and this one's pretty intimidating just at a glance. But let's take a look here. So we've got f of x equals the square root of 6 over x squared minus x to the 4th. And because I see that I've got these x's here, I'm actually going to try something interesting. I'm going to try and factor out that x to the 4th. So I'm going to factor it out like this. And the trick here is to remember that if I had a 6x to the something, over x to the something, I need this, x to the, x to the 4th over x to the something is what's going to happen here, because I'm factoring out this x to the 4th. That's a little bit confusing, I know, just give me 1 second. So we can stop and take a moment to realize that when we have, if I had, say, x a third over x squared, obviously when we're dividing expressions with exponents that have the same base, so in this case our base is x, I subtract our exponents. So this would just be x to the 1st, because that's x to the 3rd, divided by x to the 2nd, so that's 3 minus 2 gets me this exponent of 1, or just x. So we're going to apply that here. So I'm rewriting this function right here, I'm rewriting that in a way that this cancels out. So in order for this to stay a 2, I'm going to make it a 6, right? Because if I do my 4 minus 6, I'm still going to get an x to the negative 2, or just 1 over x squared. And obviously with that 6 in there. So that means that we've turned this function into this. And now I can factor out that x to the 4th, right? And remember, this is the same thing as this. I just kind of manipulated it so that it's something we can work with. So I'm going to factor out that x to the 4th, which gets me minus 1. Obviously, we know that the square root of x to the 4th is going to be x squared, right? Because x squared squared is x to the 4th. So if I take that square root, I'm just going to end up with x squared. So I can pull that out of my radical. So it no longer has any impact on my domain, because we know that the domain of x squared is all real numbers. So this x squared no longer affects our domain. So we're still just looking at what's on the inside here. Now, once again, the thing that we have to remember here is that it's going to be in our domain only if this inside here is going to be greater than 0, right? Because if we have any negative numbers, it is outside of our domain. It is undefined. So what we need to find is when this is greater than or equal to 0. And then we're just working with inequality. So I can add our 1. So we get 6 over x to the 6th is greater than or equal to 1. And then it gets a little trickier. So let's see, we get 6 is greater than or equal to x to the 6th, because now I'm multiplying that out to get rid of this in our denominator, which means that x is going to be less than or equal to the 6th root of 6. All right. So this is actually going to be our domain, but the fun thing about this is because it's going to be that x to the 6th, we know it can be even, we know that this can also include negative numbers. So we know that our x, so the outside of our ranges, our bounds, so to speak, can be this or a negative version of that, right? Because if I were to plug this in for x, since it has this even power here, this negative is going to end up disappearing, just like if I squared it. Like if I have a negative 1 squared, it turns into a 1, right? Or negative just disappears because it's an even power. So we can, so we can work with both of these. So we know that it's continuous when x is less than this right here, or is greater than this, I believe. So we know x has to be less than or equal to this and greater than or equal to this. But x can also never equal 0, because that would have a 0 in our denominator, which would be messy. So obviously there's a lot of rules at play here. So this tells us that our function is going to be continuous from, that should be a bracket because it is inclusive. So we include that. We don't include that. I believe this is going to be our interval, our set of intervals. And let's go ahead. Actually, I'm going to erase some of this work down here so that we don't have to pay attention to it. It does not want to erase fully. Sorry. I'm going to erase some of this just so we don't have to look at it anymore. And let's just double check our work. We're going to plug it back into our original function, which that should be an x squared. So let's see. If I plug in 6 And we'll plug in this first bit here just to make sure that it does meet our conditions. So I've got negative, and it's going to be squared, minus this to the fourth, which will end up being, let's see, squared, so that's going to be, I believe, no. It's going to be 2, 6. So it should be, I think that is what that ends up being, minus, let's see, I believe that's how that ends up working, because it ends up being squared, and obviously you can put that square in there. I think that's right? Because, let me double check that really quick. So if I have the 6th root of 6, that's the same as 6 to this power. And then if I have that to the 4th, that's the same as 6 to that, or 6 to the 2/3, which is the same as this, or aka this. And obviously there's nothing in here then that would give us issue, except potentially if this value is smaller than this, right? Because for subtracting. So let's double check that. So obviously it's going to be a 36. And I'm just going to double check this with a calculator since we're just checking right now. So I'm going to put in, let's see. Hold on, let me grab a calculator because I did not have it out. So we're going to put in the cube root of 6. I'm going to do 6 divided by cube root of 6, which gets us about like a 3.3019, so on. And then I'm going to take the cube root of 36, which is exactly that same answer, so this will just end up with a 0. And obviously, we were just plugging in our negative value. Our positive value should end up with the exact same thing there. So that just confirms that this is our domain set. And I'll write that over here. So it includes this up to 0, and then from 0 up to and include, oh, not negative, sorry, up to and including this. That is our domain. It's the interval for which it is continuous. Now we're going to do same kind of question, except different function, right? And this obviously has a bit of a different domain. So something that we just have to know about natural logs, and I hope you know this already, natural log of 1 equals 0, but the natural log of 0 is undefined. Anything above 0 in that natural log, say natural log of 1/2, exists, right? So that's okay, but anything less than, let's say negative 1/2, is just completely undefined. Those values don't exist. Wait, yeah, because that is outside the domain of natural log. So natural log's domain, by default, so the domain for a natural log, which is our parent function, natural log of x, is always going to have a domain of x is greater than, not equal to, so just greater than 0, up to positive infinity. Oh my goodness, it never undoes the right stuff. So this is that domain set, and that's just something that we need to know in this case. So what that tells me is that we need to figure out what in here is going to make the inside of that natural log be 0, and just make sure that our values stay larger than that. So, because it's a natural log of 2 minus 12e to the t, let's figure out what equals 0. So we know that our domain has to be greater than 0. So this ends up needing to be greater than 0, not equal to, remember, because 0 makes this undefined. So, oops, sorry, so 2 minus 12e to the t is greater than 0. First thing I'm going to do is I'm going to subtract this 2, so I get a negative 12. E to the t is greater than negative 2. Take out my negatives. Since they're both negative, I'm just going to flip that. Now I'm going to divide both sides by 12, so I can get that e to the t all by itself. So I get e to the t is greater than 2 over 12, or just e to the t is greater than 1/6. And now our t is in that exponent, so it's a little bit tricky, but we're going to pretend right now that this is an equal sign and not a greater than sign. And we're going to use our log rules. And remember that if I have this, then I also have this. And these are the same. They're just two different ways of writing the same thing. So in this case, my base is an e, so I'm going to turn this into a log base e, and this is my y equals my x, which is just t. And obviously a log base e is our natural log, so I'm going to rewrite that as t, or we know our t needs to be less than that, I believe. Yeah? Hold on. No, greater than, sorry. Greater than, what was our original function? So, let's see, natural log of 1/6. Yeah, less than, I believe. Shoot. Yeah. So our value needs to be less than that t. And so that is our t. What was the question? Our intervals. Oh, yeah. So this is our interval. That's always going to be less than our t. So our domain in that case is going to be, let's see, if this is always less than t, then t is negative infinity up to, but not including this. This is our domain. And remember, the reason we don't include this is because if I plugged this value into this equation, or into that function, that's going to make this interior equal 0. And again, natural log of 0 is undefined. Right? And I'm going to erase all of this now, just because it takes up a lot of space. Yes, just give me one moment. Oh my goodness. I don't know why it always lags when I do this. Ah, not what I meant to do. Okay. So I'm gonna rewrite our domain up by the question, actually. It's negative infinity up to this, and I forgot that extra parenthesis, actually. Awesome. Now we've just got a few questions left. And so for number 7, it says, for which of the following values does the inequality below hold? And obviously, for it to hold, it just means that it's true with whichever values. So the easiest way to do this is, quite frankly, to just plug in values. We could go ahead and figure out our domain for this, but that might honestly take longer. So let's go ahead and see. First thing I notice is if I plug in this -2 right there, that's going to give me a 0 in the denominator. So it does not work because that's going to end up undefined. So we're not going to use that one. Actually, I won't cross in there. We're not going to use that one. But let's go ahead and plug in our positive 2 then. So we've got a positive 2, which is going to be a 4 to the third. So 4 to the third, which will be positive, right? And then we've got, or 4 to the third, actually, let's see, what would that be? 4 to the second is 16, 4 to the third is 64. And then we're still just plugging in that 2, so we've got 2 times 2, which is a 4, times 2 to the 8th, or sorry, 2 to the third, which is 8, plus 1, which is 9, which is then 36 over 64. Is that greater than or equal to 0? Absolutely, because this is a positive value. So this value works. Let's go ahead and check some of our others. Let's plug in this negative 1 now. So I've got a negative 1 plus 2, which is just 1. To the third is just 1, so our denominator is 1. It's positive. Look at that, negative 1 times 2 is negative 2 times a negative 1 plus 1, which is just going to be a 0. 0 times negative 2 is 0, which is greater than or equal to 0. So that one also works. All right. Let's try our x equals 3/4. So if I put that 3/4 in the bottom here, it's going to get me 2 3/4, or I believe 11/4, which I don't actually know what it is cubed. So let me just figure that out really quick. It's going to be 121 over 16. And then times another 11 times 4 is, I know that's a 64. 121 times 11. There we go. Okay. So our denominator, oops, it's 1031 over 64 over, or not over, but under. So 2 times our 3/4 is going to be 3/2 times 3/4 cubed, which is 9/16, 27 64. So 27 64 plus 1. And we're noticing that all of these numbers are positive, which means we're going to get some positive number, which means that it is greater than or equal to 0. We don't really have to evaluate this because we know it's all positive. That's all that matters to us. So that value checks out. Let's plug in this negative 10 now. So if I've got a negative 10 plus 2, it's going to be a negative 8. And then cubed is going to be, let's think. That's going to be a negative, I think, 512. Under negative 10 times 2 is negative 20 times negative 10 to the third, which is negative 1000 plus 1. This is going to be negative. This is negative. So our top is a positive and our bottom is a negative, which makes the whole thing negative, which makes it less than 0. So it's not greater than or equal to. So this one does not work for us. And now let's try that negative 3. So I've got a negative 3 plus 2. So negative 1. Negative 1 to the third is just negative 1. Negative 3 times 2 is going to be negative 6. And then negative 3 to the third is a negative 27 plus 1. This is all going to be negative times a negative. So we get a positive over a negative, which is, again, less than 0. And therefore does not satisfy this inequality. So our answers are just these 3 values that worked for us. All right, now this next one is a pretty easy one. It says, for the following graph, which limits exist at x equals 4? And by which limits, it's just referring to our left-sided limit, our right-sided limit, or our both-sided limit, so our general limit. So in this case, we've got x equals 4, and we obviously see that our left side limit exists because it is approaching a value. There's no discontinuities in here. There's nothing that's stopping it, no asymptotes or anything, so this limit does exist. We also see that approaching from the right side, this limit also exists. So we've got a right side limit and we've got a left side limit. And because we see that they both approach the same y value of this y equals 1, so the left side limit and the right hand limit are equal, which means that our double-sided limit exists. So this limit exists, which means that all of those limits exist. So all 3. Now for this next one, it's asking us for pretty much the same thing, except with a limit at x equals -1, and a bit of a different graph here. So we're looking at this x equals -1 right here. And so we're going to look first at our left-sided limit. So it sees that it approaches a point. It has a limit. Awesome. So this left-sided limit exists. And the left-sided limit looks like it equals 1. So we'll say the limit as x approaches -1 of this function equals 1, because that's the y value that it is approaching. Now let's check our right-handed limit. We see that there is a right-handed limit. It is approaching a value. But the limit from oh, I didn't write from the left, sorry. The limit as x approaches -1 from the right in this case looks like it equals a y value of about 2, 2.5, so we'll put a 2. Well, we'll put a 2.5 because it looks like it's right in the middle there. And so obviously this right-handed limit exists, and it's got a value that we can apply to it, but we'll see that these limits have different values. The left-handed limit equals 1 and the right-handed limit equals 2.5. And because these aren't the same number, because they don't equal the same thing, our double-sided limit does not exist. This is where we would say that the limit does not exist, because the limit only exists when our left-handed limit and our right-handed limit are equal. So in this case, we don't have all 3 limits existing. We just have our left-sided and right-sided, but not our double-sided limit. And now for our very last one. It's another interesting one. We've got this function that says if f of x equals this, is the function continuous from both sides, just the right or just the left when x equals 0. So we're going to be, if we plug in a 0 here, it's obviously going to be a 1 minus 1. So this is the 4th root of this interior here, which in that case would just be 0, which that exists. Okay. But now we need to test from either side. So let's come up with a couple of values. Let's think. So we'll start with our left-sided limit. So we'll go maybe -2, -1, and then our 0 obviously gets us 0. If I plug in a -1 for this x, I'm going to get a 1 minus a 1 over e, right? Because it's going to be that negative exponent, and when we have a negative exponent, it's just, we just flip it on the fraction line. So in this case, we know that e is a little over like 2 point something, right? So this is going to be like a 1 minus, say, a 1/2-ish, which is just going to give us a little less than a 1/2 inside of our 4th root. That exists, right? So that's good. That tells us that that exists. And that's all we're looking for right now, is we're just looking if it has if it has value, if it exists. And then let's plug in our -2, so it's going to be 1 over 1, or 1 minus 1 over e squared inside of our 4th root. And we're going to get a similar thing here. We're just going to get a 1 minus a small fraction, which works out in our favor. So this also exists. So that tells us that our left-sided limit in this case, not our left-sided limit, sorry, the function is continuous from the left. So we're going to go ahead, I'm going to circle that in green so that we know that we're done with that. That exists. And now we're going to do the exact same thing, but we're going to do it from the right side. So, all right, so we're going to do it from the right side. So we've got 0, 1, and 2. Obviously 0, we know, ends up 0. Let's plug in that 1 though. So I've got 1 minus e to the 1 inside my fourth root. And again, we know e is 2 point something or another. So it's going to be 1 minus 2 point something, which is going to be less than 0, which means that we're going to have a negative inside of this. And because this is a fourth root, right, we can't have that negative in there, just like we can't with our square root, which means that this value actually does not exist. It does, I'm going to write a D and E for that. It does not exist. There's no value there. It's undefined. And that kind of tells us our answer already, but we're going to go ahead and plug in the 2 anyway, just to keep going, double check. And obviously, that's going to get us a bigger number, which means that we end up further in the negatives within our fourth root. So that also does not exist, which tells us that it is not continuous from the right. It is continuous from the left, but because it's not continuous from the right, it's also not continuous from both sides. So it is just continuous from the left. On that note, that was our last question. So we are all done with this video. Again, I know I say it every video at this point, every time, but Khan Academy is your friend. Google is your friend. Textbooks can be your friend. Sometimes they're a little bit more confusing than helpful, but they're definitely good to give a glance, especially since they'll give you more official and like descriptive definitions for things. But on that note, I hope that everybody got something from this, and yeah, this is done.